Welcome to the Explainer. Today, we're leveling up our understanding of how computers actually do basic arithmetic. We're going to conquer a concept that honestly trips a lot of people up: binary subtraction. If you've ever wondered how the silicon brain of your device crunches numbers, well, you're in exactly the right place.
So, let's dive right into this seemingly impossible task. Think about it. How can a machine that literally only speaks in zeros and ones possibly calculate complex differences? In our everyday decimal system, we've got 10 unique digits to play with. But computers? They only have 2. How in the world do they handle taking a larger amount away from a smaller amount?
Think of this explainer kind of like a video game tutorial. We're going to scaffold our knowledge through 5 quick steps. First, the 4 binary rules. Second, subtraction without borrowing. Third, the borrowing mechanic explained. Fourth, a big borrowing example. And finally, we'll look at the computer's secret trick. All right, let's kick things off with Section 1, the 4 binary rules.
Okay, here's our rule book. We have 4 primary rules for binary subtraction. 0 minus 0 is 0. 1 minus 0 is 1. 1 minus 1 is 0. So the absolute crucial takeaway here is that those first 3 rules, they're exactly like standard everyday decimal math. Totally intuitive, right? But that final rule, 0 minus 1, well, that's where the entire game changes. You obviously can't take 1 away from 0, so just like in regular math, you gotta borrow. But exactly how we borrow in binary, that's the secret to mastering this whole topic.
Moving right along to Section 2, subtraction without borrowing.
Let's warm up with a nice, clean scenario. We're going to subtract binary 1, 0 from binary 1, 1. We always start from the right column, the least significant bit. Applying our rules, in the first column, 1 minus 0 equals 1. Moving left to the second column, 1 minus 1 equals 0. And there's our final result, 0, 1. See? Just like regular math. We breeze right through the columns and the ones and zeros just fall perfectly into place. And hey, to put that into perspective, if we translate to decimal, binary 1, 1 is 3 and binary 1, 0 is 2. 3 minus 2 is 1 and binary 0, 1 is exactly that. It's 1.
Now things get a bit spicy. Section 3, the borrowing mechanic explained.
What's really fascinating here is the absolute contrast in how borrowing actually works. In our everyday base 10 system, when you're subtracting and you don't have enough in your current column, you borrow from the left, right? And that borrowed 1 brings over a value equal to the base of the system, which is 10. So a 0 literally becomes a 10. But wait, in binary, we're in a base 2 system. So when you borrow a 1 from the preceding column, it only brings over a value of 2. In binary notation, that 2 is written as 1, 0. So when you're staring down a 0 minus 1, you borrow, your 0 becomes a binary 1, 0, and you subtract 1. 2 minus 1 leaves you with 1. It's totally logical once you see it.
And mapping this out brilliantly illustrates the physical action of that borrow if you were doing it on paper. Say we're subtracting 1, 1 from 1, 0, 1. In the middle column, we hit that roadblock, a 0 minus a 1. Can't do it. So we literally cross out the 1 in the column to the left, turning it into a 0. We carry that borrowed value over to our current column, changing our 0 into a binary 1, 0. Boom! Now we can successfully subtract. Binary 1, 0, which again is 2, minus 1, gives us 1.
All right, time for the boss battle. Section 4, a big borrowing example.
Let's really see how this builds column by column, methodically moving right to left to rescue those zeros whenever they face a 1. Let's line them up. 1, 0, 1, 0 on top, minus 1, 0, 1 on the bottom. Step 1, the rightmost column. We've got 0 minus 1. We have to borrow from the column to the left. So that 1 becomes a 0, and our rightmost 0 becomes a 1, 0. Now, 1, 0 minus 1 equals 1. Moving to step 2. That next column over gave up its 1, so it's a 0 now. The bottom number is also a 0. 0 minus 0 is 0. Piece of cake. Step 3, moving left again. Uh-oh, we face 0 minus 1 again, so we borrow from the next place over. That 1 becomes a 0, our current 0 becomes 1, 0. 1, 0 minus 1 equals 1. Finally, step 4. That leftmost column gave up its 1, leaving it at 0. There's nothing beneath it, so it just stays 0. And there we have it. By successfully carrying our borrows through all the columns, we arrive at our victorious final result of 0, 1, 0, 1. But hey, let's verify our work by checking it against our trusty decimal system. The binary value we started with, 1, 0, 1, 0, equals the decimal value 10. The number we subtracted, 1, 0, 1, is equivalent to 5. 10 minus 5 is 5, right? And perfectly, Our binary result, 0101, translates exactly to 5 in decimal form. We did it! We totally defeated the boss level.
But wait, there's a massive plot twist. Section 5, the computer's secret trick.
Yeah, so here's the wild part. Computers actually hate dealing with all this complex borrowing. When engineers design processors, they realize pretty quickly that building physical circuits dedicated specifically to subtracting and tracking all that complicated borrowing back and forth across multiple bits is incredibly inefficient and expensive. So, to avoid the massive headache of building complex subtractor circuits, engineers rely on a brilliant logic loophole. This loophole allows computers to literally subtract using their existing addition hardware.
It's called 2's complement arithmetic. Instead of subtracting, the computer takes the number it wants to subtract and finds its 2's complement. First, it just flips all the bits. Every 1 becomes a 0, and every 0 becomes a 1. Easy. Then it simply adds 1 to that flipped number. Finally, by taking this shiny new 2's complement number and just doing standard, straightforward binary addition with the very first number, the computer arrives at the exact same answer. If an extra carry bit falls off the end, it just ignores it. Through this wild method, computers execute subtraction without ever having to borrow a single digit. It's practically magic.
So, we've demystified how computers process subtraction, both how we do it on paper and that sneaky hardware trick inside the actual machine. But as you take away these fundamental rules of base 2 arithmetic, I really challenge you to think about this. If borrowing in binary brings over a 2 and borrowing in decimal brings over a 10, how exactly would this exact same logic expand into the wild worlds of base 8 or base 16 computing? Imagine pulling over a whole 16 every single time you borrowed. Think about it, keep exploring, keep calculating, and we'll catch you in the next explainer.